Everyone to a new Multiview Tech Meetup edition hosted by Qualabs. Today we are going to have two great talks. First one from Alex Giladi, editor of MPEG-DASH. He's going to tell us about all the new cool stuff in the Dash 6th edition. And then I'm going to switch hats again and talk about a project also with Alex Giladi we have been working on about synchronizing thousands of players using CMCD and CMSD. So I hope you enjoy all the talks. And Alex, please, the stage is yours.
There are lots of mentions of the new sixth edition of Dash. Now that we have actually officially submitted it to the last round of ballot, let's try discussing it. So first of all, sixth edition, latest version of Dash, finished in May 2025. It's going to FDI's ballot. FDI's for the uninitiated is final draft international standard. Basically, you can fix typos. You cannot change anything of essence, and it is available at a very obscure site, DMS MPEG Expert. This is where all the MPEG documents are stored. If you don't have access, ask someone who does. It's at most a 1 Sigma community. So we're going to discuss several of the technologies. It's actually a pretty hefty update overall. So first of all, we'll talk about media presentation insertion, more known as Dash interstitials or alternative MPD. Then we'll talk about L3D Dash, slow latency and low delay, and a few more curious things like duration patterns, integration of content steering and CMCD, and some additional things. So stay tuned and awake. So first of all, alternative MPD, or how to do interstitials in Dash. So we'll start with what is guided at insertion, because we'll need this for the continuation. But we have instead of the normal client side or server side, we have an MPD that is cacheable, like in client side. It has triggers. Typically, you have 35Q CD35Q messages. Here we have triggers, for instance, alternative MPD events in our case, and they tell you instructions what to do and what are you going to get, as opposed to SCSI-35, which is pretty good in describing time periods, but not what to do. So what we end up having roughly is you have a cacheable MPD. It has triggers. It has segments. The client processes triggers. It executes an event. It asks an SGI endpoint, what should I play? And it gets an MPD back. And the SGI endpoint does some sort of magic and talks to an ad decisioning system. This brings us to media presentation insertion, which is a generic name for Dash interstitials. It consists of several things. First of all, alternative MPD events, which is another way of saying in Dash event language, please start playing an alternative MPD, which is an ad, and please come back when you're done. So what it actually contains is URL of the ad, when it should be resolved, because you don't want to go and do everything at the beginning of time or at the very last moment. Then timing information, when do we switch, for how long are we going to play this alternative content, and what to do if we cannot play it or cannot play it in time. Then there are some execution directives, same as in HLS. For instance, you can say that this ad should be only executed once, and then we're ignoring it. So this is all good, but there are several additional parts to this. There is NXI, which is actually pretty old, but it's something that became essential for alternative MPDs. It is a way of sending the client state and opaque blobs to the SGI endpoint, which we need to make in order to make things personalized while we're keeping the MPD cache. The last concept is a list MPD. So this is an ad break that contains periods, each period being a link to some MPD. We'll talk about it later. And this is an equivalent of asset list, but way more complex than just a JSON file of playlists. a couple of pictures to explain. We have the simplest option, which is just an insertion. Insertion is please go and play this alternative media presentation and come back to the place where you start. We have a prefetch interval. We're saying how early you can. So what is an insertion event? Load the MPD for the ad, and then we're saying a time PRT, which is just presentation time. We're going to start presenting that. And if for some reason we're late, for instance, we're joining after the start of the ad, we can still go and execute it at some point in the future. And there are ways of either doing it delayed or cutting it short. More interesting option is MPD replacement. So what it does is, unsurprisingly, replaces a part of content with the content described in an alternative MPD. So an event arrives. You have prefetching, same as in MPD insertion. The difference is that first of all, you can go and update these events, and this will actually take precedence. And then your main client is not paused as in insertion event. It is in a listen mode. So listen mode means we're updating the MPDs, we're processing MPD events. And then as opposed to resuming at the same place where we ended, we are actually resuming at media time RT, which can be just something that happens to be when the alternative presentation ended, or we can go and say we want this time code. For instance, if you have CDVR content and you had a 60-second ad break, now you want to insert 90. So you can go and insert 90 seconds and then return to the 60-second boundary to go and continue. Where do we start playback? It's kind of interesting. So first of all, we started at the PRT presentation time, and this is happening in most cases. We can start it a little bit later. It's called delayed execution. So we can go and start there, either because we joined late, or because we had a previous event that had overlap in time, and it only added a time PRTA, not a time PRT. And then there is an option of never to execute it, which I kind of like because I hate ads. If we're, for instance, saying that this event needs to be executed once, we execute it once. But then if we're going and seeing it again, because we went into time shifted mode, then we're not going to redo this. Additional interesting technologies, as I promised. So NXI, which can be viewed as parameter routing. You get parameters from some source. They can be reflected from an MPD URL. So you are asking for an MPD, you get a redirect to an MPD plus some, let's say, ID value based on some query parameter, and then you remember this query parameter. Another option is client state. For instance, which language are we playing right now? Now these parameters are passed with HTTP GET, typically as query parameters. And one of the options is to pass them with alternative MPD request. Why would you do this? Several things. First of all, let's say you want to assign some sort of ID to this session. You, as a deployer, are doing this in an opaque way. Nobody cares how this is done. You don't want to go and affect the cacheability of your MPD. So you go and do the through-to redirect, and then continue always requesting with this ID, and you also remember this ID value. The other thing is passing client state information. For example, that we're playing in English. It can be which codecs we're playing, what is the bit rate, and we actually needed to go and match add to the playing content in a way that will make the transition smooth. For instance, codec transition is not a pleasant thing, and it can sometimes result in black screen. We don't want that. Data bit rates we don't want to exceed. List MPD. So this is an extremely complicated way of saying what. Please play this list of MPDs. It's very simple, similar to the asset list, as we said, and the way it is generated is typically through an SGA endpoint. The endpoint asks the decisioning system what to play. The decisioning system responds, let's say with VAST, and with list of things that we need to download, and with beaconing. And list MPD, formally, it's an MPD that contains one or more linked period. What is linked period? Very, very similar to Xlink. We basically had to redesign Xlink because it had too many problems, and it was easier to redesign than to fix. So linked period contains a URL of a single period imported MPD that you download when you go and already have your list MPD returned to you as a result of the alternative MPD request. So this MPD has only a single period, and it can have additional elements and attributes. We take this linked period, we take the imported period, and we merge them, creating a normal, regular playable period. The process also a little bit resembles Xlink, but it has a much tighter processing model, both time-wise and in terms of how elements and attributes are coming from both periods. And a workflow just to put everything together. So let's say we're the client. Initially, we're getting our main MPD. We have the 302 track that we showed. We're getting MPD 0, so our first MPD. We're playing it. At some point, we're getting our ith MPD, and all of a sudden, we see an alternative MPD event. So this is when it's first seen. And we see that it has a URL of alt.mpd, and its presentation time is T0. So we'll go and request the SGI endpoint, please give me an MPD. It talks to the ADS, it translates the VAST response into a list MPD. Then it doesn't matter when, but probably very soon afterwards, we go and resolve the list MPD, which means we're downloading the individual imported MPDs and doing the merge. In the meanwhile, we can have an event update that tells us actually PRT is slightly different. It's now T0 plus T1, and this is all. We're reaching PRT of T0 plus T1, and we start playing the alternative presentation. We're still, this is MPD, this is a replacement. We're still in listen mode, and we're processing events. And at MPD, apologies, but I plus N plus M, we see that there is an update that says your maximum duration now is 0, which means please go and switch to the main playback immediately. This is also something that most of us know as return to network. So this is the overall workflow, and we end up where we started, playing the main content. Next is L3D dash. So this is low latency, low delay. That's why it's L3D, and it's low latency HLS compatible. So what was the motivation for the whole thing? Because we already have low latency dash, formerly known as Chunky Monkey. First of all, we want to do low delay. What is low delay? Normally, in any digital video system, you need to wait till the beginning of the GOP or till the ADR. So if we're using a 2-second segment and a 2-second GOP, we have to wait till its beginning. which is in the worst case 2 seconds. We want to try starting playback immediately. The next thing is add insertion without stream conditioning. So you slap an ad in a random place. You want to be able to return to it even if this happens to be in the middle of the segment, and again, not wait for up to 2 seconds. Lastly, there is a way of being compatible with low latency HLS in regular low latency dash. You use byte ranges. People tend to complain about byte ranges, having implemented or having tried to implement them. So if we want to do really good HLS compatibility, we have this discretely addressable partial segments. Also, practice shows that the latency when you use partial segments is a little bit lower, probably because nothing within the browser, for instance, knows that an HTTP chunk in low latency HLS has some meaning, and probably an end of a CMF chunk can still stay in some buffer and add delay. With that said, we want to be more efficient at low latency HLS, and we still want to maintain dash templates. So how do we implement this? Segment sequences. As a sequence is a sequence of k partial segments. They can have different properties in terms of does it start from IDR or it starts from something unknown, and they're equivalent or treated equivalently to normal single GOP segments that we use. And for example, what we can do is we have low latency HLS compatibility. We have something where you have 2 second segments, and we have 4 partial segments. Only the first one has IDR. For low delay, we can have very, very small segments all starting from IDR, and we'll look at the picture to visualize this a little bit better. In terms of syntax, you see 3 new things here. Subnumber, something that actually existed before but was never used. This tells you what is the index of the partial segment within the segment sequence. Then there is segment sequence properties, which say what starts from IDR, if any. So type 1 means subtype 1 IDR at the very first. So at the very first segment, partial segment, and we have absolutely no idea what happens on the next segments. Low delay mode. So we add 2 representations, both low delay. So we have one that has 120 millisecond GOPS, so typically 6 frames, and we have 480, which are basically 4 times larger. We start from these very small segments. We get to the 480 millisecond boundary. We go and start playing the other low delay segment representation, and once we get to 2 second boundary, we go back to regular segments. Why this is good? We're improving in best case by 1.8 seconds. Why do we need to go and do these switches? Because the smaller the GOP, the less efficient it is from the compression standpoint. So we want to go and spend as little time as possible playing it. And one important point is that it doesn't really matter what are the regular segments. They can be just what you are used to. They can be the chunked low latency dash ones. They can be low latency mode as we will see in a little bit. So the low latency HLS compatible ones. So what we have here is this low latency HLS compatible mode. Same configuration. We have 2-second, 1.92-second segments or segment sequences. We have a live edge representation that is more or less a carbon copy of low latency HLS. So partial segments. The first segment in a sequence starts with an ADR. And we have a normal time-shifted representation that is a little bit behind behind the edge, the live edge. And what we can do is eventually drop the live edge representation segments and only keep the time-shifted ones. Next, duration patterns, which is a pretty interesting and unique thing coming from Amazon Prime and Elemental. So what's the problem? We want to align audio and video segment boundaries. The reason is there are very smart implementations that start playing both audio and video at the same time. So you want to be very close together. Unfortunately, this is very easy for Europe. So we have 1.95 seconds or 3.84 seconds, where the sample durations for audio, for AC and AC3 match the ones for 50 FPS video. For US, with a 60,000 by 1001 frame rate, if I remember correctly, this is somewhere about 15 minutes. So obviously this is not going to work. So people came up with patterns. So a pattern is in current practice a sequence of n segments. It has let's say n-1 audio segments, and with x-1 samples, and then one longer segment with x samples. And the idea is that the sequence boundaries are roughly aligned with video boundaries, and on the average, this segment will be roughly aligned with video. The point is you want to make it very close, even if this does not ever match. So there are two syntactic solutions that we can do right now. The worst, the most precise, and the most onerous is you go and you use segment timeline with one XML element describing a sequence of segments. So we have one S element with n-1 segments with x-1 samples, and then another element will give you the longer segment. So the problem is you're repeating this, let's say every 12 segments. If you have a 1 hour MPD, this becomes huge, and huge means traffic, but mostly it means CPU. How much time does it take you to parse on crappy TVs? How much memory do you need to store this monstrosity? A more efficient option is number-based addressing only for audio. It's very efficient, but the problem is loss of precision, because the spec says if you don't do segment timeline, your duration that you are specifying is ±50%, has ±50% deviation. So if you are saying you have 2 second segments, you can actually legally have 1 second to 3 seconds. So you are losing precision big time. So what do we actually have now? We have, again, it's a standard 2 ways of doing duration patterns. The simplest one is we'll say what is the tolerance explicitly. We'll say, for instance, we can be ±20 milliseconds, a single audio sample, which is another way of saying this audio segment duration is between let's say 1980 milliseconds and 2020 milliseconds. The problem here is a tiny loss of precision, and some people like Amazon Prime really didn't like this. So what was introduced is an explicit pattern. So number one on your right hand shows this pattern element, which describes a pattern with 12 segments of duration 180, 480, and then one shorter segment. So this is what we describe, and then we reference this from an S element. We basically replace a duration that used to be specified in the S element with the duration of this pattern. So what we are saying here at number 2 is, here is the pattern that we're using, and PE means we're starting at index 3 within this pattern for the first time, and then we're repeating this 164 times. Next, content steering and CMCD, our favorite subjects. So first of all, content steering. What is content steering? I think this is probably a little bit rhetoric because most people here already work with it, but it's an originally it's a part of an HLS spec supported in Dash, and what it does is it provides pathways and their priorities. So this may mean CDNs to be used for streaming. So this is defined elsewhere. What do we need to do in Dash? We need to go and integrate it. So we introduced a concept of service location, which is more or less a label that can be applied to an MPD or to a segment URL, and it's equivalent to a pathway in that spec. So we need to understand which server to use. Does the client have to obey the instructions, or it's optional? And then should we start from our playback from asking the content steering server? So these are the key things. And what actually happens is we go and move from service location to service location based on what the content steering server told us. And here is an example of this. We say that we have multiple service locations, alpha and beta. We say here is our content steering server, and then the content steering server returns the JSON response below that says the priority of the pathways are alpha goes first. If you cannot get something from alpha, go for beta. CMCD. So for people who haven't encountered this, this is a short way of saying how to signal BS interoperably. So this is a CTA standard, CTA 5004, published in 2020. We're all working now on the version 2, which is expected in a few months, and it's pretty widely implemented. What it actually standardizes is a vocabulary of key-value pairs that represent mostly the client state. For instance, BS is buffer starvation or rebuffering, and not what you thought. It also specifies how are the values derived. It specifies the on-the-wire format. In CMCDv1, it's either wire parameters or headers, and it specifies the processing model. Where do we send the data and when? An illustration, wire player, we're getting a segment video.m4v, and we're beautifying the URL by including the BL key, BL being buffer length. So we're getting the video byte spec, and also we can go and look at the CDN logs and feed this buffer length to an analytics endpoint. There are other possible uses for this. I think originally the thought behind BL was maybe the CDN can optimize for people who have very low buffers, so they're very likely to rebuffer soon. But I think it's far more useful for analytics. Now, what do we need to do about it in Dash? two things: initialization, so which requests should carry CMCD. For instance, are we going for all video and audio? Do we want to go and do MPDs as well? Second thing is, what is the on-the-wire format that we want to use, query parameters or headers? And last but not the least, which keys should be reported? The next thing is deterministic behavior. Right now, if you don't do some sort of initialization, the content and the session IDs are random strings. This is obviously not as useful if you want to go and look at what happens within the deployment, because otherwise you can glean more information from these strings. What else? So two additional things. One is Multiview HEVC. This became more interesting once Apple Vision Pro happened and HLS started supporting stereoscopic presentations. So we did exactly the same thing with the MPEG-DASH. Multiview was always supported, but the problem was that what was supported was multiple tracks. So one track, let's say, for right eye, one track for left eye. HLS did everything in a different way. They multiplexed the views. So now we have a multi-track, a multi-codec track, or where we go and multiplex the normal backwards compatible, let's say, left eye view and right eye view, which is the difference between what was in the right eye and in the left eye. So this is not only for Multiview HEVC. This can be used for layered codecs. For instance, if you want to do LCVC and go and do both base and extension layer in the same track, now you can do this. And then there was a modification in stereoscopic signaling. First of all, we need to be able to say this is stereoscopic video, which funnily enough we couldn't do. And then we want to say the right eye or left eye is first. A much larger thing is ARI, or addressable resource tracks. So this is a multiplexed index, and the attempt there was to go and make something like SIDX more amenable to live. So it can indicate sizes or estimated segment sizes, and it's very convenient for things like content adaptive. Always a question comes up: was this implemented by anyone? And here is the current status. Alternative MPD implemented both for Shaka and DashJS. L3D implemented for Shaka, work in progress for DashJS, and we expect an implementation in libsim2 as well, so that you can actually simulate this. CMCD and content steering implemented in both Shaka and DashJS. Not yet implemented duration patterns, Multiview HEVC, but it's not surprising because there is no way of playing it in Dash until there are Android-based devices that can play it. And ARI. And shameless plug, there is some work going on for IBC25 and there is an accelerator project that uses much of the editions of the 6th edition. This is the rough architecture of it. We're working with RT, the Irish broadcaster, and British Telecom to play 6th edition Dash. We're doing L3D with alternative MPD events, and we have CMCD version 2, which is not yet finished, in order to go and do metrics. And we have SGI endpoint that does two things. It does the translation of alternative MPD request to go to the ADS, and translation of VAST into list MPD. And then it also uses CMCDv2 to go and do beaconing. So CMCDv2 information is in the MPDs, and then we go and do beaconing using it. So thank you so much. This is it. I hope that it didn't take too much time.
Thank you, Alex. Everyone, if you think just because of time, I will start presenting the other presentation, and we will wrap up with questions for both presentations at the same time. Okay? And thank you, Alex, again for presenting today. Synchronizing thousands of players, an open implementation using CMCD version 2 and CMSD. And this story tells that not a long time ago, the experience of watching TV, that was very different. There was only one device, and the signal reached everyone at the same time. Where that was a time where we could all shout the goals at the same time, and that's really here in Montevideo when Uruguay plays. You need to to close everything, your windows, everything, if you want to see the goals before your neighbor shouting the goal before you. And well, we know that because with streaming those days are gone, that we could always shout together. And the idea is that we are going to bring them back. Thank you, AI, for all those beautiful images that generated for me. So the idea for today is talking about the live synchronization. So it's a fun challenge nowadays, and I think you all have experience to have different playbacks experiences of latencies in devices, and it's a challenge that again it's based on multiple formats, HLS and Dash. We have different sometimes packagers and also maybe someone playing low latency Dash or low latency HLS, regular LHS, and all that. Also, players has their own buffer, and network conditions are different. Buffer targets of the player configuration could be also different, and the ABR logic may vary on those devices. So, with this in mind, Alex said, "Hey, let's try to achieve this issue, and let's try to achieve frame level or at least sub-second synchronization in for again for thousands or millions of viewers." And to tackle this problem, we will need these basic ingredients. So a common clock reference for all those players that we want to synchronize, a target latency for those players, also to know what's the latency we want them to play, and a way to exchange information between the player and the synchronization server, CDN, or whatever. So topics today. First, a quick recap about how timing works in HLS and Dash, then how to prepare the content for synchronization, then how to exchange the timing information to the players. Then we are going to talk about how to synchronize a playback session in particular, a very, very fun demo, and future work. So let's start with the recap, how timing works. In HLS, by default, you can play any HLS live content without a clock reference. This is for regular HLS content. You just need to fetch the latest segments from the playlist and you're done. And you may know that there is a special tag called the X program daytime. It's a tag that provides an absolute timestamp that you can put on the playlist. Usually you put it before an XTIMF tag of a segment. And generally it is inserted in packaging stage, and generally it could be like packager time. And again, it's an optional tag. We use this for synchronizing playback with external events data, for example, to sync with a score or stats in sports, or to allow users to seek to a specific date in a live stream. So basically, we will need this tag in our system to be able to synchronize players because it's the date, the timing information we will need. In Dash, let's remember how the player knows what segment to fetch using segment templates. So we need to solve when we have segment templates in this example, for example, we need to solve the number of the segment we need to fetch. So basically, what we do is we get the time right now, the real time from UTC timing that it's already there. For example, this is a time server from Akamai. Then we need to calculate the elapsed time since the availability start time that is over there in the MPEG-DASH. So for example, here will be the UTC, the current time minus the availability start time. And then we need to calculate the segment duration that in this example, we have so duration and time scale, and we just need to divide those values. And at last, we need to calculate the segment number using this formula over there, that it's the floor of the elapsed time divided by the segment duration plus the start number we have over there. This example, we can, for example, the availability start time is epoch is 0. We are working everything in Unix timestamps. So the elapsed time, this was from yesterday, duration, time scale. So we can have the segment duration over there, that is 2 seconds. The start number is 0, as we can see from the template. And so we can calculate from the date what segment we should fetch now to watch the content. So in Dash, by design, each segment has a time reference. And this is all we need to be able to synchronizations, because the segment by itself in this template-based Dash example has already the timing information needed to synchronize. So for preparing the content, all we need is going to be to package both HLS and Dash with the same clock reference. So we need to put to create the segment numbers and also to put the X program date time at the same time with a reference clock that could be, again, for example, that clock that we just saw from Akamai. And that's everything we will need to in the content to be able to synchronize it. Then we need to exchange the information. And if you remember from the previous talk, we have talked a lot about CMCD version 2, that now CMCD version 2 is able to send not only information to the CDN, also to third-party analytics servers. And also we have, on the other hand, we have another standard. It's called CMSD, Common Media Server Data, that it's like a cousin of CMCD. That the idea is how servers can send data back to a player using headers, some particular headers that are defined in CMSD. So the idea is, okay, if we use this pattern, we can have a way to send information from a player to any server over there. And CMCD is playback-related information, so we can send playback-related information about the player to a server, and the server can respond back information to the player using CMSD. So I think this is a very cool pattern to use to exchange information. And the idea is that, yes, we're going to use this. So in CMCD version 2, we can know the playhead time as absolute timestamp. We have a new key that it's called playhead time, that for live streams, it must be represented as milliseconds since the unique epoch. So perfect. It's an absolute clock. That's an example over there for PT. And then when we think about CMSD, CMSD supports custom keys. So you can add any key value of data that you want to send back to the player. And there's an example over there, com.example/my key, and the value you want. Using this, we are going to send the information we need to the player to synchronize. That is, we created a key called com.sbta/clock. That it's a reference clock. It will be the same reference clock that we use to package the content. And also another key that is com.sbta/latency target, that, as you expect, is the latency target we want from the player. And so this is how everything will look like. We have the packager, the reference clock, we prepare the content in HLS and Dash, then we go to a fixed CDN, and the player will use CMCD version 2 to send to send its playhead time to a remote server. In the remote server, we can see what is happening with the player, and we're going to send back the reference clock and the latency target we want. Now in the player, we are going to have a very basic and simple algorithm that is we sync with the reference clock from the CMSD information. We get the latency using we calculate the latency using that reference clock. And if we are ahead or behind the target, we're going to modify the playback rate to achieve the latency we want. And if for some reason we cannot achieve the latency or we are fine or something, then we can take on other actions. So basically, if we have here our reference clock in blue and in green our playhead time, and imagine the target is in the black one, then we're going to increase the playback rate to achieve that latency. And in the other hand, if our latency is larger than current, then we're going just to slow down the playback for some seconds. And so let's go to a very fun demo, and let's see if this works for everyone. It's going to work. So I'm going to share with you now in the chat 2 links. First one is a Dash player example, and this second one it's a Shaka player example. So let me share you the screen, change the screen so I can show you what you will see right now. Share this tab. So good. If you just open the link, you will see this. For example, I just choose the Shaka player example. So I'm playing content from LiveSim. And here you will see at the bottom the chart that shows the current latency. I have right now 12 seconds of delay. Also, I can see the buffer of my player and the playback rate of my player right now. And I will open another tab about server that is sending the information about the latency target for all the players. So right now I can see here in this chart, changing screen. I can see all of your players right now, all of your sessions, and the latency targets everyone is right now. So one thing is if you put there's people with a lot of latency right now. But in theory, if you can, don't put the tab into background, because in background the player will go increasing the latency. So if you can, just put it like aside, and we will see everything better here. So basically here I'm putting all the players. Let me share my screen so you can see both examples by your screen. This is better. Good. So here I can see the latency that is registered by everyone. And also, look, this is what happened when I put also the player in background. And here I can see all the latency of you. The red one is in background right now. And a lot of sessions over here are exactly in the target that we want. And for example, if I say, okay, now I don't want everyone to be in 12 seconds. Let's say that I want everyone in 8 seconds of latency. So I just update the latency. The player will send a CMCD version 2 request. The CMSD will say, hey, now the target is 8. And the playback rate will increase and my latency will go down. And this is how this mechanism works. I will clean here the chart. So we will see, yes, a lot of people being in the target latency, more people that has in background. I will fix that for the next demo. And people who is right now going down latency to achieve the target. So also something important, of course, this is open source, and you can see over there the link, and you can download whenever you want to try by yourself. And as future work, we have two things to keep going. One is to work in the logic in the player. For example, we can try to like having sync latency ladders. For example, for players that could not achieve certain latency, and we want them to fill in some bucket of latency, and better logic for the player for what to do on buffer starvation. What happens if I'm trying to put some latency that the player cannot achieve? I in the server use CMCD version 2, the reported information, because it's all information from CMCD, to have to calculate what's the best target for a population. And I think that's also very, very important to know. I want to thanks to all the team that have been working on this, because it's a very, very fun prototype. Mainly Alex Giladi, Emil, Juan Manuel, Constanza, Sebastian, because it is not just this prototype, it's also building all the CMCD stuff needed to achieve this communication way using CMCD version 2 and CMSD. And thank you. Questions about this and Dash 6?
I have a question. Well, Nicholas, earlier this year, I worked with a customer who had some interesting streams. And one thing I learned, and I went all the way to the HLS interest group and asked Roger Pantos, the timing in the EXTX program date time and the timing in the segments are completely independent. So, for example, it turns out, surprisingly to me, that it was legal HLS to have, say, two EXTX program date time tags that were, say, 15 minutes apart and had no segments in between them, or maybe only had 10 seconds worth of segments in between them. How do you handle that kind of insanity in your control loop?
I don't know. So in the example we show, as we are controlling the timestamp we're putting for the X time date, the tag. So we have full control right now with that, because yes, we know we are putting from the clock we want. So discontinuities will for sure impact, because that's the clock we need to synchronize. So that's a very good question. If someone wants to use, I would say that right now, or the answer I can give you now is, for this prototype, it will only works, of course, if we have control of the clock. And I think that should be the thing.
Okay. Yeah, the interesting thing in the spec is those are two completely separate clocks, and they aren't allowed to be mixed. And my customer who had these streams discovered that the Shaka player devs hadn't read that part of the spec, and they were trying to, do math combining segment time durations with EXTX program date time, and that's where things went awry.
Yeah, sounds a complicated scenario. Great, thank you, Ben. Any other questions for Alex or for me, or ideas how to use this? If
Alex,
not, yeah, go for it.
Alex, the patterns. I love the patterns. How long do you go before you have to cut a period and resynchronize audio and video?
I would probably go until you accumulate up to 40 milliseconds, and then go and cut. 40 milliseconds is so if you go and get to a loss of AV sync, it won't be noticeable below 45.
All right. Well, I'm a timing aficionado, so those are my questions.
If there are no more questions, Thank you everyone for being here. Thank you, Alex, for the presentation. Super excited about all the Dash new things. And see you in the next one, everyone.